Hello. In tonight's video, I'm going to be talking about R and S designation in stereochemistry. So R and S designation is part of nomenclature, which is just the set of rules that allows chemists to talk to each other about what a molecule looks like. And I typically don't spend much time on this in class because most organic textbooks do a pretty good job of covering it on their own. But one part of that, this R and S designation, I think is actually really important, and it's kind of hard for students to see. And so I want to make a video about it. So the world that we live in is three-dimensional, right? But if I draw a molecule on the board, it looks two-dimensional. We'll make this one a nitrogen. And so by drawing on the board, I've lost some information. I've lost how it looks in 3 dimensions. Okay, and so in the real world, it has some kind of 3-dimensional shape. And it turns out that all of nature has these 3-dimensional shapes and that they have very specific ones. And so that when a small molecule, like this molecule I've drawn, is interacting with a biological system, like you or me, it matters what it looks like in 3 dimensions for how those two things interact. So it's a lock and key is what's commonly used as the analogy, and that's that enzymes or proteins have a very specific shape, and for anything that's going to fit inside of them, it also has to have a similar shape. This has all kinds of really interesting repercussions when we get into biochemistry, okay, and if you think about the world around you. So if you were to eat something like a protein that was made synthetically with the wrong stereochemistry, okay, the wrong shape in 3 dimensions, the opposite shape of what the natural world is, your body would metabolize it differently. Okay, your body wouldn't be able to break it down the same way because it wouldn't fit into your enzymes the same way. And sometimes we actually trick your body that way, and we trick your taste buds that way to make things that taste sweet that your body can't break down as sugars. The other time this is really important, or one of the big examples of this was the drug thalidomide. So thalidomide was a drug that's very good at stopping morning sickness in pregnant women. But it turns out that there's a stereocenter in thalidomide, and one of the stereocenters, okay, so one of the enantiomers of that drug, is really good at stopping morning sickness, stopping nausea, and the other one caused profound birth defects, okay, caused limb deformations. And no one knew that there was a difference in these enantiomers until babies started being born with these birth defects. And so even if you drew the thalidomide flat on the board like this, it would look exactly the same, both enantiomers. But because you've drawn it flat, you've lost that really important information showing you that those 2 enantiomers were actually shaped differently. Okay, so that one of them was good as a drug and the other one had very unfortunate consequences. And so through this, it's very important that chemists are very clear not only about how the atoms are bound together, okay, so that's what this shows. This is a very clear representation that I have a carbon bound to a carbon that's bound to these 3 atoms. But I also need to be able to show you what that looks like in 3 dimensions. And so what we typically use for that is a wedge and dash drawing structure, such that if I put something on a wedge, it's coming towards me. And if I draw it as being on the dash, it's going away from me, okay? So now that I've drawn this, I've drawn in the stereocenters, but I need a way to communicate that stereocenter to someone else, okay? And so we use R and S for that designation. Now, one of the things that you need to be able to do, okay, is assign whether or not a stereocenter is R or S. But before you can do that, you have to be able to figure out which carbons are actually stereocenters. So we're going to watch a short video where I can show you what a stereocenter is. Okay, a stereocenter has to be a carbon that is sp3 hybridized. Okay, it has to have 4 different things attached. And then those 4 things, again, all have to be different from each other. Okay, so if 2 of the things are the same, then it's not a stereocenter. And so if you have a carbon with 4 different things attached, its mirror image is the opposite stereocenter. So if you have those 2 things, they're mirror images of each other, Like your hands are mirror images. Okay, so my hands fit well together like this, but there's no way for me to lay my left and my right hand on top of each other such that they're exactly the same. Okay, because my hands are chiral. My hands are mirror images of each other. And so the mirror images, even though they look the same and they have the same connectivity, they're not the same and they can't be overlaid. Okay, so we're going to watch a video where I can show you that so you'll maybe understand better the difference in the two stereocenters. And then we're going to come back and I'll show you how to assign a stereocenter once you've found one. Okay, so these two molecules are our enantiomers. These are both carbons. Okay, and the carbon on both atoms is attached to the same things: a red atom, a blue atom, a green atom, and a white atom. Okay, and so the connectivity is the same. If we didn't have any information about how they looked in 3 dimensions, we would think that they were the same. And if we imagine a mirror plane right here, then you can see that these two molecules are actually mirror images of each other. Okay, so the blue is coming towards us, and the blue is coming towards us, and the red is going away, and the red is going away. Okay, so these two are mirror images of each other. So even though they look the same, they're different stereocenters. And if we try to overlay them with each other, we'll see that there's no way to overlay them. Okay, so even if we put them together and we spin them, we're still not going to see them ever line up. Okay, so we overlay them. There's no way to rotate this molecule such that all 3 atoms line up. Okay, we always have 2 mismatched because they're stereocenters. They're not the same molecule. They're fundamentally different. And that's why it's important for us to, 1, recognize that they're different, and then be able to label them so that we can communicate that information to other people. Okay. So now that you have in your head a little bit better what a stereocenter is and how they're different from each other, I want to show you how to assign a stereocenter in a molecule. So I'm going to draw us up an example. And then we'll assign the stereocenters. And I'll show you a couple tricks along the way. So here's our molecule, okay? This molecule contains 2 stereocenters. This is a stereocenter. And this is a stereocenter. There's a dashed hydrogen here that I'm not showing, but I'll draw in now, and a wedged hydrogen here. Okay? So this carbon has 4 different things attached: an oxygen, a hydrogen, a carbon, and then another carbon with some different things. So it's sp3 hybridized and has 4 different things attached. So it passes the rules for a stereocenter. This carbon is not a stereocenter because it has 3 hydrogens attached. Okay, these 3 hydrogens are all the same, and so there's no way for me to assign an R or S designation. So let's talk about the R and S. R and S designation comes from the Latin, rectus for right and sinister for left. Okay, so that's R and S. And the way that we assign these, okay, because it's a nomenclature rule, because it's something that we made up to make our lives easier, the rules are not based on size, they're not based on anything in the physical world, they're based on atomic number. So the atom bound to the stereocenter that has the highest atomic number is going to be the highest priority. And so between oxygen, hydrogen, and carbon, oxygen has the highest atomic number, and so it's the highest priority. Okay? And we're going to assign priorities to everything that's attached to that carbon. Now next highest priorities is going to be carbon, but I have 2 of those. And so whenever you have a tie, you just start to look at the things that are attached to that tie. So this carbon has 3 hydrogens attached, and this carbon has a carbon, a bromine, and a hydrogen attached. So the bromine has a higher atomic number than hydrogen, and so this carbon is assigned the second highest number, okay, the second highest priority. Now I have to decide again between carbon and hydrogen. So the carbon is the number 3 priority, and then the hydrogen is number 4. Okay? So the first thing to do is assign the priority to all 4 atoms that are attached to the stereocenter based on the atomic number. Once we have that, we're going to draw an arrow that connects the 1, 2, and 3 priorities. So we go 1, 2, 3. Now my arrow is going to the right, okay? My arrow is going to the right, and so this stereocenter looks as if it is R. If it's going to the right, it's R. If it's going to the left, it's S, okay? Left and S. So it's going to the right, so it's R. Before I make my final decision, though, it's important that the lowest priority is on a dash. If the lowest priority is on a dash, then the stereocenter is the way it looks. So this is an R stereocenter. Okay? Now we're going to see that's a little bit different on the next one, so let's do it again. On this carbon, we have, again, it's sp3 hybridized, and we have 4 different things attached: bromine, carbon, hydrogen, and carbon. But these 2 carbons are different from each other because this carbon only has 3 hydrogens on it, whereas this carbon has oxygens and other things. And so of these 4, bromine has the highest atomic number, and so it is the highest priority. Now again, I have a tie between these 2 carbons. This carbon has only hydrogens, this carbon has an oxygen, and so it gets the second highest priority. Now I have to choose between carbon and hydrogen. Carbon has the next highest priority, and then hydrogen. So I've assigned the priorities, and now I'm going to, again, draw an arrow to combine them. 1, 2, 3. This stereocenter is also going to the right, so it looks R. But the lowest priority is on a wedge, not a dash. If the lowest priority is on a wedge, then we're going to flip the stereocenter. Okay, so this stereocenter is actually S. We figured out our priorities. We drew an arrow to see what the stereocenter looked like. It's going to the right, so it looks R. But the last thing we do is we check to make sure that the thing with the lowest priority is on a dash. If it's not on a dash, we flip it. If it is already on a dash, then the stereocenter is exactly the way it looks. Now there's one other situation that you might find, and that's if the lowest priority is on the line. So I'll give us another example. Okay, so here my lowest priority is on a line, okay, and so now I can't use my trick. I can't just assign them and call it what it looks like, and I can't assign them and flip it, okay? If the lowest priority is on a line, you have to actually rotate that stereocenter to get it either on a wedge or on a dash. So here's how I do that, okay? We just need to rotate it. And so I'm going to redraw the structure, just the lines and the wedges and the dashes. And then what I'm going to do is I'm going to pretend like I'm holding the molecule from the top, holding it still by that methyl. So methyl is going to stay on the top. And then I'm just going to take it and I'm going to rotate the whole thing, holding methyl still on the top. I'm going to rotate it 1 position. And so if I do that, then hydrogen is going to move over onto the wedge. Bromine is going to move back onto the dash. And oxygen is going to swing around and now be on the line. So now that my lowest priority is on either a wedge or a dash, then I can use my usual tricks. Okay, so now we need to assign all of the priorities. So bromine has the highest atomic number, followed by oxygen, followed by carbon. 1, 2, 3. This appears to be R, but my lowest priority is on a wedge, and so I'm going to flip it, and this is an S stereocenter. Okay? That's much more challenging to see from here. You kind of have to try to like hold it in your head and do it from this side. While you're learning, it's much easier to just take a second and redraw it And then you can use your normal tricks, okay? Assign priority, draw your arrow, either R or S, and then decide based on the priority of the lowest, based on the position of the lowest priority, whether or not you need to flip it, okay? So R and S designation, like I said in the beginning, it's really important in the real world. Real world chemists use this all the time. And as you continue in organic chemistry, you're going to come across reactions that either maintain that stereocenter or flip the stereocenter, okay, depending on the mechanism. And so you're going to need to be able to assign stereocenters and change stereocenters as you go through organic chemistry. So this is a really basic concept that it's really worth the time to master now, so that when you're doing more complicated things, this part is second nature. So feel free to watch the video as many times as you need to and keep practicing, and I hope it helps.